Hey guys, Mr. McKinney here, just going through concavity and points of inflection. So when we refer to concavity, a function would be concave up when the slope is increasing. So when the rate of change is positive. And when we're looking at concavity, we're going to be looking at the second derivative of the function to figure out whether a function is concave up or if it's concave down. And if a function is concave down, that happens when the slope is decreasing, when the rate of change is negative. So again, we're looking at the rate of change, so we're looking at the second derivative. The first derivative will tell you if the original function is increasing or decreasing. The second derivative will tell you if the original function is concave up or concave down. And you're going to look at when the second derivative is positive or when the second derivative is negative. So if f double prime is positive, then we say it's concave up. If f double prime is negative, then we say it's concave down. And if it's 0 or undefined, that's where you're going to have a possible point of inflection, and we'll get to that in a little bit. So the way you can remember it, concave up, it looks like a cup. So if it's concave up, it's going to look like a cup. So you're going to see kind of like a smiley face pattern when a function is concave up. If a function is concave down, you can remember it's going to be kind of like a frown. So if a function is concave down, it's going to look like a frown. So concave up looks like a cup, concave down looks like a frown. And if we go back to what the definition of it means, so a function is concave up would look like this. So maybe you're going from negative slope to 0 slope to positive slope. So your slope could be positive or negative, but the whole time the slope is increasing. You're going from steep negative slope to shallow negative slope to 0 slope to positive slope. So as long as the slope is increasing, it's concave up. You don't have to have the whole U shape to be concave up. You can just have something like that, and that is still concave up, even though you don't have the whole shape. Same idea when it's concave down. So if something is concave down, it doesn't mean the slope is negative. It means that the slope is decreasing. So you can have positive slope, less positive slope, 0 slope, negative slope, more negative slope. So if it's concave down, the slope is decreasing. And again, it doesn't have to be the full U shape. If you're any part of that, then you would be considered concave down, as long as the slope is decreasing. All right, let's do a couple of quick examples. So determine if the function is concave up or concave down at the given value. So we're going to look at the second derivative. So here's our original function. We're going to find the first derivative, which would be 4x cubed plus 9x squared minus 18x minus 23. And then we're going to find the second derivative, and that should be a lowercase f. So 12x squared plus 18x minus 18. And basically we're just plugging in x equals 2, x equals negative 1, and x equals negative 2. So what is f double prime of 2? What is f double prime of negative 1? And what is f double prime of negative 2? So we're just plugging in each of these values. So 12 times 2 squared plus 18 times 2 minus 18. Let me check my notes here. That's going to be 66. And that means that when x is 2, the function is concave up. So let's check when x is negative 1. I look at the second derivative. So I plug negative 1 into the second derivative. And if I check my notes, we're going to get negative 24. So a negative value means that it is concave down at that value. And then at negative 2, so again, just plug in negative 2 into the second derivative. And this would give me negative 6, also a negative value. So again, it would be concave down. So if you want to know if a function is concave up or concave down, you look at the second derivative. If you want to know if a function is increasing or decreasing, you look at f prime, not f double prime. F double prime is for concavity. Increasing or decreasing is f prime, or the first derivative. All right, Now let's have you guys do a couple of examples on your own. So given g of x, figure out if it's concave up or concave down at each of those values. And then for h of x, figure out if it's concave up or concave down at each of those values. So go ahead and hit pause, and then we'll see how you do. All right, here you go. So for this first function, you would have gotten that the first derivative is equal to 3x squared minus 12, and then the second derivative would be 6x. So you're just looking at these different values. If I plug in positive 2, 6 times positive 2 is a positive number, so we're concave up. If I plug in negative 3, we're going to be concave down, because g double prime of 2 is 12, g double prime of negative 3 is negative 18. G double prime of 0 is 0, so we're neither concave up or concave down. And this is where we're going to have a possible point of inflection, and we'll get to that in the next video. For h, for the first derivative, you should have used the quotient rule, and then you would end up getting 6 over x plus 4 squared after you simplify it. Now you can use the quotient rule again, or if you rewrite that as 6 times x plus 4 to the negative 2, you can use the chain rule and the power rule to get your second derivative, which would be negative 12 divided by x plus 4 to the third power. Now in this case, when you plug in your different values at x equals negative 5, h double prime of negative 5 would be positive 12, so it's concave up. If I plug in negative 3, h double prime of negative 3 is going to be negative 12, because down here you're either just going to have positive 1 or negative 1 cubed, and then dividing negative 12 by that. So here a negative value would mean this is concave down. And again, if I plug in negative 4, I'm going to be dividing by 0, so it's undefined. Sorry, h double prime of 4 is undefined. And since the second derivative is undefined, that means it's neither concave up or concave down. So again, we're going to say that it's neither. And again, this is going to be a possible POI, and we'll get to that in a second. All right, so again, the second derivative is what you're going to be looking at when you want to figure out if a function is concave up or concave down. Graphically, concave up looks like a smiley face or a cup, and then concave down looks like a frown. And that's how you can remember those names. All right, hope this was helpful.